In this problem 4.12 from the book of Theory of Vibrations with Applications, 5th edition from Thompson, we are asked to find the response for a triangular pulse as shown below. We can work this problem by using the superposition principle, which applies for a linear system. And we can divide the problem in intervals, like for example, here the time goes from 0 to time 1, but we can divide this problem by first analyzing this section here that goes from 0 to half the time, and using the convolution integral, which is the same as saying superposition integral, to solve the problem. Now, the equation for the superposition integral is of the following form. The superposition integral is equal to xt is equal to 0 to t, the integral from 0 to time function, and the function for the response of a unit impulse. So this is the response to a unit impulse. So these items, we can identify the function first. The function is already given in the problem for each time interval. So you can notice here, this section here is Fe. And H is already defined for a spring mass system with no damping. So for a spring mass system, with no damping, we know that H, the response to a unit impulse, is equal to the following formula. Okay, so let's first analyze the interval from 0 is to half t1. So 0 is less than t1 over 2. So that this is the interval that we're going to be working on, which is this section of our drawing from 0 to half t1, because from here to here is the whole time. Okay, from that interval, the function is equal to 2f0. F0 is the amplitude here over time 1 by t. So let's substitute that in our convolution integral, and we're going to get that x1t, and I say x1 because we're in this first interval of time, is going to be equal to the integral of 0t. The function that is already given is 2f0t, but we're going to be working with epsilon as the integral variable, so we're going to substitute here for epsilon t1, wn over k sine wn t minus epsilon, and integral about that. Now, we have defined our convolution or superposition integral. So all we need to do from this point and on is to do the integral and get the solution for the first interval. So to do that, let's put the constants outside. So we're going to be, everything that is constant is going to get outside of this integral. I'm going to have the integral of 0 to t epsilon sine wn t minus epsilon. So note that this integral has two functions, so we can use the integration by part process to solve this integral. So let's do that. So we recognize that the integration by part process has the form of this. So we have the integral of u dv dx equals uv minus v du dx dx. So all we need to do is to identify what is u, what is v, and be able to solve this integral. So if I set u equals to epsilon here, then du is equal to 1 delta epsilon. And if I said that dv dx equals to the sine of wn t minus epsilon, then first of all, notice that I need to integrate these to get b, right? So notice that the integral of a sine wn t minus e, if I use the u as a substituting variable, this is going to be equals to the integral of cosine. I'm sorry, this is going to be equal to cosine wn over wn t minus e. And be aware that this is coming by substituting using the u substitution on this, so we can that's why we get a positive cosine w. So let me just write it over here. The integral of sine wn t minus epsilon is equal to cosine wn over wn t minus epsilon. And again, it's positive because when you substitute here with the u substitution, you're going to work this integral only. You're going to see you're going to get this value. Okay? So now we have that information there. So now let's just substitute all of these variables in our integral, and let's get what is going to be the result of the integral. So now we're going to substitute these values on the original equation, and we're going to get that epsilon multiplied by cosine wn over wn t minus epsilon minus the integral of cosine wn over wn t minus epsilon dE, which is substituting in the partial fraction equation to solve the integral, and all of this evaluated from 0 to t is going to give us the answer to the problem. Okay, so first let's now solve this part. And in this part, notice again, if you use u substitution, you're going to find that the integral of cosine is going to give you minus sine wn over wn, and there is another wn here, t minus epsilon. Okay, that's the result of this integral using the u substitution here. Okay, now we have to solve all of these, so let's just put this all together. And now we have epsilon cosine wn over wn t minus epsilon minus sine wn. Just put this a little bit up so you can see. Sine wn t minus epsilon over wn squared, evaluated from 0 to t, is going to give us the result. So let's do the evaluation from 0 to t, and we're going to get something on the following form. So we're going to get epsilon cosine wn t minus t, and plus sine wn t minus t over wn squared minus, now we're going to evaluate in terms of 0. Okay, let's put this a little bit up. Let's evaluate now the integral in terms of 0, and we're going to get the form something like this. So when we evaluate the integral above, we get 0 multiplied by cosine wn t minus 0 over wn. And now we get plus the sine wn t minus 0 over wn squared. So this is going to be the other part. So now let's just simplify the whole equation down here. And we're going to get, so notice this is cosine 0, so this goes to 1. Sine 0 is 0. So let's simplify this, e by 1 wn, right? Sorry, this should be t, because we need to substitute t on e here. So this is going to be t, 1 wn, and this is 0 plus 0, minus, and let's go to the second part of the integral, which is over here. And we're going to see we have minus. This term goes to 0, and then this term is simply the sine wn(t) over wn squared. Now let's just express this here, sine wn(t), this is w, over wn squared. So this is going to be t over wn minus sine wn(t) over wn squared. And all of this we need to multiply now by the constant that we have, so that we took out of the integral, which is 2f0 wn t1k. Now let's do this multiplication here. And we're going to get something of the form down here. So let me just rewrite this down here. 2f0 wn over t1k multiplied by t over wn minus sine wn(t) over wn squared. So now doing this simplification, let's put wn and t1 inside. So 2f0 over k t wn over wn(t1 minus sine wn(t) over wn squared multiplied by wn over t1. Okay, simplifying this further, we can get, see, so this is what we get when we put wn and t1 inside, we get this equation. And we want to simplify this a little bit more. So we're going to get something like this, 2f0 over k multiplied by t over t1 minus sine wn(t) over wn t1. And this is our result for x1 t, the solution for the first interval of time. So now, let's rearrange this a little bit more by recognizing that wn is equal to 2 pi over period, right? So wn is equal to 2 pi over period. So if we substitute these in here, we're going to get, the expression is going to become as follows. So now we have x1t is equal to 2f0 over k, and then we have t over t1 minus sine 2 pi over tau by t, okay, and then 2 pi over the period by t1, and then this is going to be equal to s1t is equal to f0k multiplied by t over t1 minus tau over 2 pi t1 sine 2 pi over the period by time. And this is the solution for x1 t. Now, because these, using the principle of superposition, we can find the other values of x2 for the second time interval and x3 using the following equation. So we just need now to simply sum all of the different pulses and clean up the system, and we can find that if you have x1, which we found x1, x2t is going to be equal to x1t minus 2 times x1, t minus 1/2 t1. This is the second time interval. And then if we want to find x3t, it's going to be equal to x2t plus x1t minus t1. And this is for t1 less than t. This is the third interval. And the previous interval was when we have 1/2 t1 is less than t is less than t1. Okay, is the second interval.